Lesson 5, black holes are attractive. Suppose a 45,000 kilogram satellite, which is not that heavy, asteroid, which is not that heavy for an asteroid, is traveling at 5.67 times 10 to the fourth meters per second at a distance of 1.2 times 10 to the seventh meters from the center of the Earth. From the what? So the first thing I noticed, that 1.2 times 10 to the seventh, it's an R, not an altitude, so I can use that if I need to. How much kinetic energy would it have if it impacted the Earth? Dean, what's this want me to find? Am I going to start out by writing down work equal? Did it say work at all? So what's this going to be a job for? I think conservation of energy. So it's going to be K E initial plus P E initial equals K E final plus P E final. Are any of these zeros? Kinetic energy would be if we're at rest. Are we ever at rest in this question? No, we didn't start at rest. And, oh, we're definitely not ending when we hit the Earth at rest. It's going to have kinetic energy on impact. What about potential energy? Isn't potential energy zero on the surface of the Earth? Not if we go cosmic. It would be if we were out at infinity. Are we starting or ending out at infinity? Okay, well then, what are you asking me to find, Dean? Let's get the KE by itself at least. KE final, I think. So I guess KE final is going to be KE initial plus PE initial minus PE final. I think we would subtract that over. Yes? Yeah. Well, okay, let's start crunching. KE final is going to be a half little m VI squared plus negative big G big M little m over RI minus negative big G big M little m over R final. I think that's right. Aiden, do little m's cancel? No, if I had said find the speed and you turned kinetic energy final into a half mv squared, then the little m's would cancel. That's not what they asked here. I do have a minus minus at least, which is a plus, so yay. I think I'm going to probably do each of these terms separately. So, Aiden, I've scrolled down. It's going to be 0.5. What was the mass, Aiden? 45,000? And the initial speed? Say it louder, please. Sorry. 5.67 times 10 to the fourth. Don't forget the squared. And then minus big G Earth, right? 5.98 times 10 to the 24th. 45,000. Aiden, what's our initial? Do I need to add the radius of the Earth to that, or they told me from the center of the Earth? Okay. And then plus same thing times same thing times same thing. But this time, what am I going to divide by? What's our final? Yeah, this is a little different. Instead of starting on the Earth and going away, this time our final is the radius of the Earth. We're ending up on the Earth. 6.38 times 10 to the sixth. I don't think I would try typing this whole line in one fell swoop. I think I would do each of these terms individually to about 5 sig figs. This is KE final, Mr. Dueck. So I would do the 0.5 times 45,000. .5 times 45,000 times 5.67 scientific notation 4 squared. So it has 7.2335. That's a good place to round off. Times 10 to the 13th joule. Wow, that's a lot. 7.2335 times 10 to the 13th minus. Is that right? Same number as me? Marcus is looking puzzled. That's why I'm a little worried. Yeah? Fahim got it right? Now I'm worried. Okay. Negative 6.67 Scientific notation, negative 11 times 5.98. Scientific notation, 24 times 45,000 divided by 1.2. Scientific notation, 7. Minus, I'll go 1.4957, 1.4957. 1.4957 times 10 to the, did you figure out where you zig, Marcus? 12th plus, by the way, the reason these numbers are also so big, 45,000 as our mass, that's larger than what we've used for satellites. That's a big mass. So we're getting large amounts of energy. Same thing, but I delete the negative and I make the bottom 6.38 times 10 to the 6th. 2.8133 times 10 to the 12th. Did I make any mistakes, or anybody else, everyone else matching me? Ruby, you got the same thing? Okay. You I trust, not Fahim. Okay. Well, let's add these together. It's going to be 7.2335 scientific notation 13 minus 1.4957 scientific notation 12 plus, haha, answer button. Let me double check to make sure I haven't made any typos because I don't want to have to retype this. See what you get. Ruby, I got 7.37 times 10 to the 13th. Yeah. Is that a lot of energy? Well, to put it in perspective, I looked this up. So the atom bomb that exploded over Hiroshima, the first atom bomb detonated on Earth, had 6.3 times 10 to the 13th joules. This is 7.4 times 10 to the basically, this is about the size of a small atom bomb. It would do some damage if it hit the Earth. Oh, how fast would it be traveling at impact? Okay. Ke equals a half mv squared. Aryan, how would I get the v by itself? And then, yeah, don't forget the square root. Okay, you know what? We have our answer button sitting here. I'm going to be really, really lazy. I'm just going to go straight to the punchline. I'll call that v imp for impact. What did you say? Times by 2, divide by m was 45,000, right, Aryan? And then square root. I get 57,200 meters per second. So, asteroids can do damage. We already are fairly certain that one wiped out the dinosaurs, which had been a very successful life form for hundreds of millions of years, far longer than us. And of course, there's the asteroid that's due to hit us in 2036. You haven't heard about the asteroid that's due to hit us in 2036? You don't watch? Wow, people. Wow. Okay. Put your pencils down, look up. I guess. Let's talk about the asteroid.
Yes, in the middle. Just speak up and you won't need the microphone. She didn't forget that asteroid. She didn't forget the asteroid. So you want a quick update on the asteroid?
There's an asteroid the size of the Rose Bowl
A football stadium.
headed towards Earth. It's called Apophis, named for the Egyptian god of death and darkness. It wasn't coincidental that it was named that. When this asteroid was discovered in December 2004, its trajectory was calculated based on a short segment of its orbit, because you look from one day to the next, it's in a new place in the sky. These folks are moving. Once you saw that its trajectory would intersect the orbit of Earth, you don't name that asteroid Bambi or Tiffany, right? You're going to give it a name befitting its
Sense of gravity.
yes, yes. That pun was surely intended. So, the reason why you never heard of it, perhaps, is because it was discovered that this aspect of its orbit was calculated and reported on the same week of the Indonesian tsunami.
So in 2004, right around when you were born or shortly before you were born, there was a massive tsunami. It was on Boxing Day. It killed 250,000 people. Well, that took up the first 30 pages of every newspaper of the day at that time, because back then we still read newspapers. That made the headlines. So this asteroid was relegated, to page 60.
Okay, I think it was end of '04 or '05. I forgot which of the
Boxing
years
Day,
it is.
'04.
Same week. Odd thing is, of course, like 200,000 people died in that tsunami. Odd thing is, if this asteroid hits in a place where it could hit, and I'll describe that in a minute, it will hit in the Pacific Ocean. It would create a tsunami in the Pacific Ocean that would make the Indonesian tsunami look like a street puddle that slightly over-spilled its edges. So I think rightly the media attention was given unto the Indonesian tsunami, but that was not an excuse to then never have the press talk about this object. It's a real object. And there's something called the keyhole. It'll have a close approach to Earth in the year 2029, in April 13th.
Which is,
Which, by the way, is a Friday.
oh yeah.
It will come close enough to Earth to dip below our orbiting communication satellites. For that passage, that will be the closest, largest thing we have ever observed.
It'll make the front newspaper headlines in 2029.
In the history of our observing the universe. That's a shot across our bow. The uncertainty in its orbit at this moment is such that for that passage, there is a range of orbits it could have, which if it goes through what we're calling the keyhole, Earth's gravity on it will be just right. Or rather,
Just wrong.
just wrong. That the next time around, it will hit Earth. 7 years later, April 13th. If it goes through the center of the keyhole, it'll hit the Pacific Ocean 500 kilometers due west of Santa Monica. It'll plunge into the Pacific Ocean to a depth of 3 miles. At that depth, it will explode, cavitating the ocean with a hole 3 miles wide, 3 miles deep. That impulse will send away a tsunami wave that will basically wipe out the entire west coast of the United States and the east coast of Asia. Now, oceans don't like having big holes in them. So this 3 mile high wall of water does what? It's a hole in the water. What does it do? Falls back in the hole. Hoses here. We're talking. It won't just stay there, like in the movie. It'll fall back into the hole, slosh into itself, rise high into the air, fall back to the ocean, cavitate the ocean again. And it'll do this with such ferocity, it'll repeat itself about 50 times, taking about an hour. So every time it cavitates the ocean, it sends another tsunami. So it won't be just one wave like the Indonesian tsunami was. This will be 40 waves, 50 waves. Now, each wave has to pull back out to get ready for the next one. and they're separated by about a minute. So there's a limit to how far these waves will get on shore. We think it's about a quarter of a mile. So if you're more than a quarter mile inland, you can just watch this happen. If you're not, now, the $1 million Malibu homes, they will feel this first tsunami wave. The tsunami will basically pick up the homes. It'll bring them back out to sea. Then the next wave will come and return the home to the shoreline. But now the home is in a slightly different shape. And as this continues, all man-made objects along the coastline and trees and debris basically becomes this churning, ablative mass, wiping clean the entire coastline. Now, nobody has to die, because we'll know this well in advance. But I found there are two people who will die. There is the stupid surfer who says, I gotta do that tsunami wave, dude. You know they're gonna be out there. Okay? So we'll have dead surfers and dead weathermen. You've seen them. There's the camera guy over there. Look closer, watch the hurricane smash into it. Get this shot, can you see this? I'm reporting from the hurricane. Scientists. If this asteroid goes through the keyhole, there'll be people evacuating the West Coast, building shelters, stockpiling food. There'll be people praying to their gods. There'll be people doing all things. I'd rather be doing something about it. This is where engineers come in, physical scientists, physicists and astrophysicists. So we've got top people right now working on a way to deflect the asteroid. Therein is the power of science. You don't have to build a shelter from something that could kill you. You can prevent the thing from killing you in the first place. It's like, how do you solve acid rain? Let's have acid rain proof umbrellas. No. You want to stop the rain, all right? How is your brain wired for finding solutions? So, there you have it. So we'll monitor the news at that time. By the way, it is not known who will pay for that deflection mission if it comes to pass. Probably America, but asteroids can hit anywhere in the world. In the UN, while there's a space unit of the UN, there's no funding stream. Suppose this were headed for Indonesia. Would we pay for that to deflect it? And suppose we pay to deflect it and we only half deflect it, then hit somewhere else. That's an interesting geopolitical problem. So it's not just fix it and go home, it's more complex than that. Oh, by the way, you got these guys who stockpile nukes, and that community want to blow the sucker out of the sky. There's the folks who want to use the nukes that we have. And the problem is, here in America, we're really good at blowing stuff up. We're less good at knowing where the pieces go after the explosion. Whereas when you deflect something, you can monitor your progress all along. But another question?
So that was from 2008, I think, that video. Since then, we do have better observations. The likelihood of it passing through the keyhole and then hitting the Earth in 2030, what was it, 6 or 7, 2035, is pretty much zero. It's technically not zero, but it's not something I'm worried about. But the 2029 passage will be spectacular. You won't be able to see it during the daytime. Asteroids are not reflective at all. They're very, very dull. In fact, I don't even know if you'll be able to see it at night unless you're getting the sun's reflection on it just right. But definitely, it'll make the news. Example 2, geosynchronous satellites maintain their orbit over the same place on the Earth at all times, usually somewhere over the equator. What's the period of such a satellite? We talked about this. I showed you the video. Earth does not have a period of 24 hours. That's a lie. It's it's from your formula sheet. The period is 8.61 times 10 to the fourth. Is that right? I'm going from memory. Yeah. If you go 24 times 60 times 60, you'll get 8.64 times 10 to the fourth seconds. That is how long it takes the Earth to rotate and pick up the sun again. That's a solar day, but the Earth spins on its axis in less time than that. So, what does B want me to find? Ashley, what does B want me to find? And I think orbital radius, because I see the word orbit. So I think we can say, you know what we can say? Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals, don't forget the little m. What did I find in part A, Ashley? I'm going to use the one with the period at the 4 pi squared r over t squared. Does a little m cancel here? Does an r cancel here? No, not in this one. In fact, I think I'm going to get an r cubed if I multiply the r squared from the bottom to the top. What are they asking me to find, Ashley? Oh, let's get the r by itself. How will I move the t squared over? I agree. How will I move the 4 pi squared over? I agree. That gives me an r cubed. R what? R cubed. What's my final step going to be? Oh, we get to use the cube root button again. Oh, this is such a good day. So r is going to be the cube root of big G, big M, t squared over 4 pi squared. Let's see if on the test write out the numbers, but in our homework, let's see if we can go straight to our calculator, because this is the mass of the Earth, which we've typed a bunch in big G. So it's going to be, if you want to type this in one step, you can, but you'll have to put it in brackets. Big G, 6.67, scientific notation, negative 5.98, scientific notation, 24, times 86,100 squared. I wrote it in non-scientific notation. Divided by, in brackets, 4 pi, don't forget the squared, close off the bottom, close off the cube root. I think that's right. Should get 42152615.6, I think. 4.22 times 10 to the 1, 2, 3, 4, 5, 6, 7. Quite a ways from the center of the Earth. 4.22 times 10 to the 7th meters. Let's talk about, or let's continue with black holes. Suppose a spaceship is orbiting a black hole at an orbital radius. I see the word orbit twice. I'm going to remember that that gives me some options. The black hole has a mass of that. What's the gravitational field strength at this radius? Ooh. Kyle, what's this asking me to find? And Kyle made the classic mistake that drives me crazy. Did you hear what he said? Force. No, it's not. This is not going to be an F. This is not going to be a Newton. What letter? What's our abbrev for gravitational field strength? Little g. It's asking me to find little g. And the only formula that I have for little g is that. Oh, you know what that's saying? Take the universal gravitation force, big G, big M, little m over r squared, and cancel out what, Kenta? You were zoned out. You're back with me now. Cancel out what? Little m. This ends up just becoming big G, big M over r squared. The little m that's part of the force of gravity would get canceled out by the m that's in the bottom of the fraction there. This is gravitational field strength. We're near a black hole. I'm guessing it's going to be bigger than 9.8. Let's find out. I'm not going to bother writing big G. Mass, 6.8 times 10 to the 32 divided by 8.8 times 10 to the 9th. Don't forget the squared. What's the gravitational... Oh, I like this question. I like this question. I like this question. What's the gravitational field strength at this radius? $587? 585.7? No? I got a nod from Eric. Yeah, okay, okay. 500, all right, 586. I think I said 587. 586 units, Kyle. I would accept meters per second squared or newtons per kilogram because it's an acceleration as well. Okay. Oh, would this be fatal to those on board the spaceship? How many G's is that? How do you change an acceleration into G's? Physics 11. Who remembers? Really, we did a whole lesson. We saw Colonel John Stapp. We saw the rocket sleds. How do you convert an acceleration into G's? You're right. What? It's divided by 9.8. So answer button divided by 9.8. How many G's? Would this be fatal? Yes or no? Why is the answer no? What? They're orbiting. Are they feeling the gravity at all? No. Okay? Not while in orbit. Now, where it would be challenging is when they came into orbit or when they left orbit. So really, for me to make this work, we would have to have some kind of Star Trek transporter technology that can beam the ship there at the correct speed. Then you'd be fine. Once you were there, you wouldn't feel the gravity at all. Now, you would have to take into account probably that if you were standing upright relative to the black hole, the gravitational field strength on your feet and on your head would be different. So it would be, I'm kind of glossing over a little bit, but yeah, if you're in free fall, you wouldn't notice it that much. You're in orbit. Ooh! What's the escape velocity required to leave the black hole's gravity well? So for escape velocity, we solved that by that was conservation of energy, right? You may have memorized it, but if you've forgotten, it was kinetic initial plus potential initial equals kinetic final plus potential final. But what were both final energies? 0. We ended up with a half m v initial squared plus negative big G big M little m over r, not final, Mr. Dueck, initial. We ended up with this. A half m v initial squared equals positive big G big M little m over r initial. Was it 2 big G big M over r square root? I'm going from memory now a little bit, but that's how we can derive it. Oh, I like example C. I like example C. In fact, you know what? I'm going to be blatant. I'm probably going to ask you to find the gravitational field strength near a black hole and the escape velocity from said black hole. Because again, I dream of space travel, and so let's go big or go home, right? Oh, I've forgotten the numbers. What was M, Mr. Dueck? You know what? I can probably get away with a little cheating here. Let's see. I have big G, big M, and R. You know, if I just delete the squared, and if I insert a 2 times, it's going to be a square root of that. I think. You get 3210635 and change? Or am I wrong? Fahim nodding? Brandon, yeah? Okay. 3.21 times 10 to the 6th. In the movie, am I wrong? Is that, I'm seeing squinting face. Is that wrong? Aiden, did you get that okay? Yeah? So you're wrong? Oh, sorry, I didn't. Okay. You figured it out? How many have seen the movie Interstellar? It came out a few years ago. Near the end, Matthew McConaughey falls into a black hole. And that's where the movie becomes completely unscientific. What would it be like to fall into a black hole? Let's pretend that you've jumped out of your spacecraft feet first. So you're going to be like a pencil, like you're cliff jumping. Okay. Well, at first, it would feel pretty good because as you got nearer the black hole, the tug of gravity on your feet would actually be stronger than the tug of gravity on your head. And so it would stretch you a little bit. And stretching, like in the morning when you wake up, feels kind of good, but very rapidly it would start to approach a medieval torturer's rack of stretching. The difference of the force of gravity on your head and on your feet would stretch you and stretch you, and in fact, eventually you would bifurcate. You would split in half, probably around your belly button. And then each of those pieces would bifurcate and bifurcate and bifurcate as you continued to fall further and further, because each of them would eventually have a force between the top and bottom that was stronger than the molecular bonds that held them together. Not only that, though, Einstein teaches us that the force of gravity warps space-time. Not only would you be bifurcating, but space-time itself would be funneling in, would be getting narrower and narrower. You would be extruded like toothpaste through a tube. All of your molecules will be funneled into this smaller and smaller and smaller funnel. And we have a name for that. We have a word for that. Does anybody know the word that astronomers have coined for the process of falling into a black hole? It's a great word. Someone whispered it. They were right. This is spaghettification. Little Italian in there for you, yeah, like that. Spaghetti. Okay? We call that spaghettification. You basically get split up vertically into smaller and smaller pieces, but space-time itself is also compressing you horizontally into a narrower and narrower region of space. And sorry, Interstellar, you're not surviving. You're just not. Got a couple more, we're done, right? I'm going to finish the unit off today. So tomorrow we'll mark the take-home quiz. You'll get take-home quiz number 2. We'll mark that Thursday. But basically, tomorrow and Thursday, the homework is also going to be start working your way through the ultimate review. Black hole has a mass of that. Suppose a spaceship is 9 point blah, 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 blah. What's the gravitational field strength? You know what? We just did this. What was gravitational field strength, Eliana? Not force. What was our symbol for gravitational field strength, Eliana? What letter did we use? Little g, and it was, as I wrote it on your formula sheet, that, which really just means take the gravitational force equation and cancel out little m. Yeah, you know what? Let's be bold. Let's see if we can go straight to our calculator. Fahim, on the test, please write out the numbers so that I know what you're typing, so I can give you part. Because if you get it wrong and you notice lots of errors in typing these in, I can't give you any part marks for the rest of it. If I can see you had the right numbers, then I just take a half mark off for the typo. So let's go to our calculator. 6.67 scientific notation, negative 11 times, what's the mass? 7.2 times 10 to the 31 divided by 9.6 times 10 to the 9th. No, wow, times 10 to the 9th, and don't forget the squared. Did y'all get 52.1? No, yes? Nods? So smaller than the previous black hole, or maybe we're further away. I have to look at the numbers. What's the escape velocity? Okay. Escape velocity was... Ooh, Kate, what was escape velocity? Do you remember? Ooh, you know what? I have big G, big M over R squared on my calculator right now. I'm just going to delete the squared. Insert a 2 times. It's nice knowing where your insert button is. If you don't know where your insert button is, it's second function delete. I guarantee it. That's where it always is. And then square root. Oh, that's a bit faster than light. Yeah, square root of that. 1.00 times 10 to the 6th. Basically 1,000,000 meters per second. That's a fluke. Is that right? At what radius from the center of the black hole does the event horizon begin? I'm not going to ask you this on the test. I may have put this one in your study, in your ultimate review, but I'm not going to ask you this on the test. But for what it's worth, okay. Ruby, what's this asking me to find? The event horizon is when your escape velocity is bigger than light. We're going to start off with the escape velocity equation. But we're going to get the r by itself. What's the r inside of? A square root? How do I get rid of a square root? First thing I would do is square both sides. And when I do that, I'll get v squared equals 2 big G big M over r. Where is the r right now? On the... Yeah. I'll get r equals 2 big G big M over v squared. And then to find where the event horizon begins, I'm going to let v equal c, the speed of light. This time, because it's new, I'll write out the numbers. R is going to be 2 big G. Ruby, I've scrolled down. What was the mass? 7.2 times 10 to the 31. Thank you. All over 3 times 10 to the 8th squared. What'd you get, Brandon? 106,000? Is that right? 107,000? Aiden, is that what you got? So 107 and then a bunch of junk, but 107,000 to 3 sig figs? That would be a radius, units, meters. In other words, for that star to have become a black hole, it would have needed to collapse and collapse and collapse, and it would become a black hole once all of that matter, once all of that 7.2 times 10 to the 31th kilograms was compressed into an area less than 107,000. That's when suddenly the star would wink out. You would no longer see light escaping from it. Is that a big black hole? Well, put your pencils down. Come on, computer. This one's pretty cool. So people often ask, how big would the sun have to be to become a black hole? You would have to crush it beyond its Schwarzschild radius, the event horizon radius that we just found. Or if you crush the Earth to about the size of a small peanut. Are there bigger black holes? Yeah. So this is X. This is one XTE and a bunch of numbers about the size of Manhattan. So it's the size of Manhattan, but it has the mass of 3 or 4 of our suns. That's nothing. Size of Mars. roughly the mass of 1,000 of our sun. It's a meh black hole, mid-range. Go big or go home. So this is the central black hole of the Phoenix cluster. That's the size of our solar system for comparison. What's its mass? It's not the biggest. It was. It held the record for a while, but we have since found a few that are larger than that. So we have a black hole at the center of the Milky Way, Sagittarius A star. Yeah, they can get pretty big. The video said that the sun would have to become the size of a small town for it to become a black hole. We call that its Schwarzschild radius. It's the same math as finding the event horizon. In other words, it's going to be R equals, what was it, Mr. Dueck? The square root, no, not square root, 2 big G big M over V, 2 big G big M over C, the speed of light squared. So now we're going to use the mass of the sun. You might even be able to just backspace and edit and change the mass of whatever was on your screen to the mass of the sun. What was the mass of the sun? 1.98 times 10 to the 30th, is that right? Am I wrong? Am I right? Yeah, okay, so 2 times 6.67 negative 11 times 1.98 times 10 to the 30th divided by 3 scientific notation 8 squared. And you get basically 3,000 meters, 3 kilometers, the size of a pretty small town. Well, about from here to the low heat highway, right? If you compress the sun to that tiny distance, that's when suddenly you would see it wink out of, not out of existence, you would no longer see any light coming from it, because to get out of that gravitational field near that area, you would need to be going faster than light. Pause.